check L ratio of span to effective depth maximum is equal to 20 into Kt into Kc into Kf. Find the LD provided. LD provided shall be less than ratio of effective span to the effective depth that we have provided should be less than the ratio of effective depth to the effective span to the effective depth maximum value, that should be less than. This will satisfy the limit state of serviceability. And then write the summary of design and draw the neat sketch. So, to explain the concept of doubly reinforcement, so dear student, let us take one example. Numerical problem is there. Design a rectangular beam 230 mm into 600 mm over an effective span of 5 meter. The superimposed load on the beam is 50 kilonewton per meter. Effective cover to the reinforcement is taken as 50 mm. Use M20 concrete and Fe 415 steel. So, in solution, given B, width of beam is 230 mm and effective span L is equal to 5 meter. Superimposed load 50 kilonewton meter. Now, effective depth is equal to D is equal to overall depth minus effective cover. Overall depth minus effective cover. Overall depth is 600 mm and effective cover is 50 mm. So, by subtracting 50 from 600, we will get 550. This is the effective depth. FCK 20 Newton per square mm for M20 concrete, and for Fe 415 steel, the characteristic tensile strength of steel Fy is equal to 415 Newton per square mm. Design of factored load. First of all, we find out the self weight. This is 230 in, if we convert into meter, 0.23 meter into 0.6 meter multiply by 1, because we are taking per meter, and 25 kilonewton per cubic meter is the unit weight of RCC. In Newton per meter cube, it is 25,000 Newton per cubic meter, and in kilonewton 25 kilonewton per cubic meter. So, superimposed load is 50 kilonewton per meter. Total load, self weight plus superimposed load, 50 plus 3.45, 53.45 kilonewton meter. Then we multiply this total load with the load factor, that is 1.5 for live load or dead load. So, multiply this 50 total load to the 1.5 and we get the factored load or design load. This is equal to 18.175 kilonewton per meter. Design the moment, bending moment and design of shear. Bending moment is equal to Wu, where Wu is the factored load, L is the effective span, Wu L square by 8, and this will bending moment is equal to 250.55 kilonewton per meter. Then find out the shear force. This is equal to Wu into L by 2, and that we get 200.4 kilonewton. Limiting moment of resistance, Mu limiting is equal to 0.36 FCK BXU maximum into D minus 0.42 XU max. So, for Fe 415 steel, the maximum depth of neutral axis is equal to 0.48 D, and 0.48 multiplied by 550, we will get the maximum depth of neutral axis is 246 mm. Put the value. FCK is equal to 20 for M20 grade of concrete. B is the width of beam 230, and the maximum depth of neutral axis is the 246, and D is the 550 and 0.42 XU multiplied by 246. The limiting value of moment of resistance we will get here. Then check Mu is greater than Mu, limiting value of moment of resistance. Therefore, beam is designed as a singly reinforced beam. So, then calculate the value of mu2. Mu2 is equal to mu minus mu limiting. Mu is the bending moment. This is 250 into 55 into 10 to the power 6 minus this, and we will get the value of mu2. Then find out the value of d dash by d, where d dash is the effective cover for compression reinforcement, d is the effective depth, and 50 divided by 550, this will we get 0.9. From table for d dash by d 0.1, the value of FSC is 353 Newton per square mm. Then find the value of compression steel, area of compression steel. ASC is the area of compression steel. This is equal to mu2 divided by FSC into d minus d dash, where FSC is the stress in concrete at steel level, and put the value, and we will get the area of compression steel 388.6 square mm. Then use 16 mm dia bar and find out the area of one bar. This is pi by 4 into d square, pi by 4 into 16 the square, we will get area of one bar. So, 201. So, then we have to calculate the number of bar. This is equal to total area of compression steel divided by area of one bar, number of bar 1.93, and we will take 2 number of bar. Provide 2 number 60 mm dia bar as a compression reinforcement. Total area of compression reinforcement is provided 402 square mm. Area of tensile steel. So, firstly we find AST1. AST1 is equal to mu limiting divided by 0.87 Fy into d minus 0.42 xu max, where mu limiting is the limiting value of moment of resistance, Fy is the characteristic tensile strength of steel, xu max is the maximum depth of the neutral axis. From this we will get the value of AST1. Similarly, AST2, mu2 divided by 0.87 Fy d minus d dash. Fy is the characteristic tensile strength of steel, d is the effective depth, d dash is the effective cover for compression steel. So, from this we will get the value of AST2, and then by adding these two value AST1 plus AST, we will get the total area of tensile reinforcement. The total area of tensile reinforcement is this 1508.3 square mm. Then use 20 mm dia bars. Area of one bar is pi by 4 into d square, diameter the square. This is equal to 314 square mm. Then calculate the number of bar. That number of bar is equal to total area of tensile reinforcement divided by area of one bar. This will come 4.8. Say 5 number of bar. Now provide 5 number of bar 20 mm dia bar as a tensile reinforcement or as a tensile bar. Total area of tensile reinforcement provided is 1570 square mm. Out of these two bar are curtailed at this distance 0.8 L, that is 0.8 into 5400 mm from the support. Then check for deflection. Percentage of steel PT is equal to percentage of tensile steel PT is equal to 100 AST upon BD. 100 into 1570 into divided by 230 into 550, this will come 1.25. PC will come 0.31%, FS is equal to 231. From this we will calculate the value of KC, KT, and find out the value of ratio of effective span to effective depth. Maximum value is equal to 20 into KT into KC. So, 20 into 0.9 into 0.19, we will get the value of the ratio of effective span to the effective depth, maximum value of effective span to effective depth 21.36. So, provided that what we have to provided L upon D is equal to 5000 divided by 55909. This value is less than 21.36, hence OK means this will satisfy the condition of deflection. Design of shear. First we find out the value of Vu, shear force, nominal shear stress, shear force divided by Bd. So, this will nominal shear stress is equal to 1.58. So, check out the nominal shear stress is less than the maximum shear strength of concrete 2.8 Newton per square mm, hence our design is safe. Now, now 2 bar are curtailed, the area available near the support is equal to 3, the area of 3 bar. So, this will 942 square mm. So, percentage of steel of tensile steel of available near the support is equal to 100 AST upon BD. So, 100 into 942 divided by 230 B, D is the 550, and we will get the percentage of tensile reinforcement available near the support is 0.75. For M20 concrete and PT is equal to 0.75, TC is equal to the shear strength of concrete is equal to 0.56 per Newton per square mm. Now, the nominal shear strength is the greater than the shear strength of the concrete, then there is need of shear reinforcement. So, shear force for which shear reinforcement is required, this is equal to Vus, and Vus is equal to total shear force into TCBD, where TC is the shear strength of the concrete, B is the width of beam, D is the effective depth of the beam, and we will get the shear force, this shear force for which shear reinforcement is to be provided. So, provide vertical strip, 2-legged vertical strip at 8 mm dia. So, spacing of vertical strips is SV is equal to 0.87 Fy ASV into D upon Vs. So, this we will get 154 mm, say 150 mm. Spacing as per normal reinforcement SV is equal to 0.87 Fy ASV cross section area of the vertical strip divided by 0.4 by 394 mm. Maximum spacing is 0.75 D, 0.7550 is equal to 412.5 mm and 3 mm. So, spacing between the vertical strip should not greater than 300 mm, 412 mm and 394 mm. Overspacing is 150 is less than all these three values. Hence, provide 2-legged 8 mm dia bar vertical strips at 150 mm. So, this is all about the design of doubly reinforced beam. Thank you.